Hi everyone, this is the first of 3 short videos on design-based and model-based inference. These are concepts that will become important when we discuss designing snow leopard surveys. The goal of these 3 videos is to explain the differences between design-based and model-based ways of estimating abundance, and when you should use each. In spatial surveys, the job of survey design is to tell us where we should sample. To do that, we first need to answer 2 questions. Firstly, what do we want to estimate? Typically, this will be something like animal density or abundance, but some surveys are set up to test the relationship between, for example, animal density and prey density. Different research questions might need different designs. The second question is, what is our survey region? The survey region, roughly speaking, is the area we want to make inferences about. We'll need to define the borders of our survey region before we design our survey. Once we've answered these 2 questions, we can use survey design to tell us where we should put our samples. To talk about the specifics of survey design, we're going to use the following simple example. Imagine that there are 51 plots arranged next to each other. Each plot has got a certain number of animals in it. For example, the first plot has got 8 animals, the second plot has got 11 animals, the 5th plot has got 16 animals, and so on. Now, we don't know how many animals are in each of the plots, but what we'd like to know is how many animals there are in total across all 51 plots, but without visiting each of the plots and counting how many animals there are. Imagine that we can only visit 6 plots, and from these 6 counts, we want to work out how many animals there are in total across all 51 plots. Now, if you look at the numbers in each of the plots, you might notice that the numbers on the left tend to be fairly small, and the numbers on the right tend to be fairly large. That is, there's a generally increasing trend that as x increases, the number of animals also increases. For now, we're imagining that we don't know anything at all about the survey area. Later on, we'll come back and see how our survey design might change if we have some inkling of this trend. This is just a slightly different way of viewing the data, where the animal counts are on the y-axis, but remember, we don't know these. If we're using design-based inference to estimate the total, we start by setting up a random sample. The easiest way to do this is with simple random sampling. With simple random sampling, we randomly choose 6 out of the 51 plots, and each plot has the same probability of being selected. Say, for example, we land up choosing the following 6 plots. If we add up the sample counts across the 6 sites, we get 18 plus 30 plus 29, and so on. That gives us a total of 273 animals across our 6 survey sites. That's obviously a terrible estimate of the total across all 51 sites, which, if you remember, was 2,429. Intuitively, the reason for this is that we need to upweight each of our survey observations to account for the fact that we're only sampling some fraction of the total area. The amount that we need to upweight each observation by is given by the inclusion probability. The inclusion probability is the probability of including each potential sampling unit in the survey, including the ones that you didn't end up choosing. Here we had 51 sites, and we chose 6 of them totally at random, so the inclusion probability is 6 over 51 for any plot. If we take our observations, our observed counts, and divide each of them by 6 over 51, the inclusion probability, we land up with a design-based estimate for the total number of animals in the area, 2,320. This is much closer to the true answer. A sample where inclusion probabilities are known beforehand and used to build the sample is called a probability sample. The only way to do correct design-based inference is with a probability sample, so you need to know the inclusion probabilities. Just remember, here we had 51 sampling units, and we chose 6, and each unit was equally likely to be selected, so the inclusion probability for each unit was 6 over 51. Because we've used a random sample, if we did the survey again, we'd end up with 6 different sites, and therefore a different estimate. Imagine we'd redid the survey and landed up with these 6 sites. Now the estimate, using the calculations from the previous slide, would be 2,406. I've got the previous estimates in here just for reference. This makes an important point about design-based inference. Variability in the final estimates comes from the randomness in the design, specifically that we've chosen sites at random. Because we choose sites at random, there's always a chance that we might land up selecting sites that have all high or all low values. Like here, we've landed up choosing 6 sites where the animal counts are pretty high, and we land up with an estimate that's much larger than the true value. This isn't necessarily a bad thing, because with random sampling, we're equally likely to be too high or too low, and so on average, we're unbiased. But it does mean that there's a certain amount of variability in the final estimates. Here I've made many random samples, and for each random sample, worked out the estimated total. The histogram plots the distribution of the estimated totals over 5,000 random samples, and you'll see that most of our estimated totals lie between 1,300 and something like 3,700. The true value, 2,429, is shown with the red line, and the mean of the estimated totals across all 5,000 samples is shown by this dashed grey line. The dashed grey line sits right on top of the red line, so on average we're unbiased and we get very close to the total. However, there's a lot of variability, so a lot of uncertainty involved in our estimates. The reason for this is that we've only used 6 sites to work out a mean, and the mean worked out from only 6 observations doesn't contain a lot of information. If we had a bigger sample size, the variance would go down and our estimates would become more precise. The last thing to say about design-based inference is that it's not possible without inclusion probabilities and a probability sample. Say, for example, I lived at x equals 20, and I decided to sample the 6 plots that are closest to me just for convenience. If you remember from a few slides ago, the calculation that we used when working out a design-based estimate of the total, we took the sample counts, I'll just write down the first 2, and we upweighted them by the inclusion probabilities. Here, it's not clear at all what should go into the inclusion probabilities, because we haven't chosen the sample randomly. So to summarize, in design-based inference, it's the design that does most of the work. The calculations of variances and confidence intervals around the estimates come from inclusion probabilities, as well as sample data. They can't be calculated without these inclusion probabilities. That means that the design has to come from a probability sample and include some elements of randomization. Inclusion probabilities, remember, are the probability of including each potential sampling unit in the survey, including the ones that you didn't end up choosing. A probability sample is a sample where the inclusion probabilities are known beforehand and used to draw the sample. Finally, randomization means setting up inclusion probabilities and then choosing sites according to those probabilities. Sampling in favorable areas, but then treating all sites as equally likely to be chosen, will bias the estimates. In later videos, we'll see how you can build in judgments about favorable areas, but for now, it's important to realize that if sites are treated as a simple random sample and equally likely to be chosen, then they really should be.